Hi everyone, my name's Erica Wright. I'm an education specialist at a place called the Center for Astrophysics. Thanks for joining me today as we explore the universe with robotic telescopes. I'm excited to have you join along with me. I'm gonna share my screen now so we can get started. Hopefully everyone out there can see my slides. So like I said, we're going to explore the stars with robotic telescopes today. And along the way, learn how we can use these telescopes to promote STEM interest and enable authentic inquiry amongst our young people. If you have any questions for me, obviously there's the community online where these are posted, but you can also email me directly at erica.wright@cfa.harvard.edu. I love getting everybody's questions. That's one of my favorite parts of my job. All right, so like I said, I'm at a place called the Center for Astrophysics. I just want to give you a little bit of background of where I'm coming from and where all this material that I'm going to share with you comes from. So the Center for Astrophysics is actually a collaborative organization. It's both the Harvard College Observatory and the Smithsonian Astrophysical Observatory. And this center is a state-of-the-art, world-class astronomical research center. So we're studying everything from black holes to the sun and everything in between. We have telescopes that our center runs on mountaintops across the world. And we have a specific center called Whipple Observatory in Amato, Arizona, that actually has a visitor center. So if you ever find yourself in Arizona, they'd love to have visitors once we're all back to going to work again. We also run the Chandra X-ray Observatory's data center. And so if you've heard of Chandra and Hubble, it's one of NASA's great observatories. And so that data actually comes through our center as well. There's also state-of-the-art engineering and instrumentation development happening at our center. So lots of really exciting, interesting science all around astronomy happening where I work. I happen to work in our science education department. Our science education department has a couple different focuses. We perform research, large-scale research studies to better understand how we're preparing students for college and what kinds of things we can do in high school and younger to change their preparedness as well as their interest in science. We also are developing curriculum and support materials for teachers, things like exhibit spaces for museums and activities and resources for both in-school and out-of-school educators across the United States. So today, as we walk along today, I hope we've got a couple learning objectives out for you. One is I hope you'll increase your understanding of technology as a tool for doing science. And I hope that you'll increase your knowledge of basic astronomy and space science content. Our goal with our telescopes is that you don't have to be an expert to come use them and to explore with your students, that anybody can start taking images with our telescopes and learn along the way. So to get this done, today's agenda, we're gonna have an introduction to the micro-observatory telescopes, one of which is on the screen now. We're all gonna take our own images. You'll follow along and take one at home yourself. We're going to do that in something called the Observing with NASA portal. I'll walk you through that steps. And then we're going to talk about an activity called Kinesthetic Telescopes. It's an opportunity to kind of get up and moving. Obviously, we are not in a classroom space today, so we're going to talk ourselves through what that would look like, and hopefully we'll get a sense of it. Then we're going to get a brief introduction to image processing, a critical step for scientists in looking at astronomical data. And then I'm going to share with you some teaching resources and sample curriculum and activities, as well as a special portal for educators in both informal and formal learning spaces to engage their students around astronomy. So all of this kind of comes down to what we like to call the Astronomers Toolbox for the 21st century. So that's robotic telescopes. Scientists, just like us, aren't often going out to the telescopes and putting their eyes to an eyepiece. They're using robotic telescopes, putting their requests in online and getting those images back, whether that be from the satellites like Chandra X-ray Observatory or ground-based telescopes that they're just not going out to anymore. They're using digital images and processing those digital images. All images are numbers. I'm going to learn what that means in just a bit. and they're doing the same things that we're going to be doing. And then there's online communities and spaces to explore and talk about that science. There's formal spaces that our scientists are using, and maybe some less formal spaces that we're going to talk about using today. So like I said, we're going to talk about using the Micro Observatory Telescope Network. But before we dive into that, I want to ask you a question and actually have you take a quick pause and write down your answer. What does a telescope do? So take a second, step back, write it down. I'll wait for a minute, pause me if you need to, and write down kind of what do you think of when you hear the word telescope? What does it actually do? Okay, hopefully you paused me and wrote something down. So like I said, we're going to focus on our micro observatory telescopes. Our telescopes are actually 6-inch telescopes, 6-inch aperture, meaning the opening, how big the opening is, that record images on a digital detector. So they actually have a digital detector just like what's in your phone, measuring how much light falls on it. And they allow users to select a target. So using both a main camera and a finder camera, which you can see here in the front of our telescope. Hopefully you can see my cursor. So this is the 6-inch aperture. So they gather and focus light. But a really important part of telescopes is that they let light fall onto the detector. You can think of them as buckets, and they're gathering as much light as possible in those buckets. And we'll kind of better dive into what all of these things mean in just a second here. All right, so we're actually in a second going to go off and take our own images. That's going to be at microobservatory.org. I'm going to walk us through kind of the key steps, and then we'll actually go to the website together. So if you have two screens, or you can break your screen up and kind of have me small and follow along. So when we get there, we're going to request an image. We're going to go to the control telescope space and pick an image that we want to take. And when we choose our object, we're actually going to have three things we're going to have to tell the telescope to do. We're going to have to choose a field of view, an exposure time, and a filter selection. So when we're talking about the field of view, we're talking about how much space, how much of the night sky are we going to be taking a picture of. And so our telescope takes everything from a normal view, what we call a normal view, which is about 1 degree, up to a wide view, which is 10 degrees. And so a normal view is about 1 degree. And if you actually hold your pinky up at an arm's length and close one eye and cover something up in your room, or maybe if you go out to your window later and look at the night sky, however much your pinky nail is covering up, that's about 1 degree of the night sky. And that's how much of the night sky we're looking at in our images. If you make a fist, that's about 10 degrees. So that gives you a sense of how large our night sky is. And when we talk about 1 degree, if you were to stack your pinkies one on top of the other like this, right? 1 degree would take 360 of those to make a complete circle around you of the night sky. So that's one thing we're gonna all have to choose when we choose our object. We're gonna have to choose the exposure time, or how long the shutter stays open. So the longer you leave the shutter open, the more light falls on your CCD detector. So think about whether or not you're looking at bright objects, something like maybe the moon is pretty bright in our night sky, or dim objects, something like we're going to get an opportunity to take pictures of galaxies and nebula, and those are pretty dim in our night sky, meaning you want to collect more light from them to be able to really see them. So the exposure time tells the telescope how long to stay open. Once that light falls, it's going to fall on something called a charged coupled device, or a CCD. And that's just like the detector in your phone. It counts how many photons of light fall on each pixel. But our detector only measures black and white, just whether light fell on it or not. It doesn't tell you what color that light was. So in our telescopes, we've installed something called a filter wheel. These filters are they are light blocking, so or light passing, sorry. So our red filter only lets the red light through. All other colors of light get blocked. So when I'm talking about colors of light, when you think about a prism that maybe somebody has at home, if you pass white light through it, it spreads out into a spectrum like a rainbow. Our filters only let the red light from that light come through. So, and the green filters only let the green light through, and the blue filters only let the blue light through. If you're able to take images in all three of these separately, you can actually do something called a true color image, which I'm going to talk about briefly later. All right, so I'm going to jump out of my presentation for a second, and we're going to go to Micro Observatory and take an image together. So if you want to go to www.microobservatory.org, like I am here in this screen, you can follow along. When we get there, there's actually a number of portals to explore our telescopes. We're gonna, some for studying things like exoplanets, but today we're gonna use Observing with NASA. This is a free online telescope space. Anybody can access it. You can all come, take as many images you want. There's no limit. So send your students, come yourself, take all the images you want. And our first stop is gonna be Control Telescope. Like I said, there's a number of objects you can take images of. We actually sort these to help our students better understand how the universe is organized. So our first section is the solar system. So things in our astronomical neighborhood, things like the moon, Jupiter, the sun. I'm gonna give you a little secret. The moon's really cool to look at. The other planets are actually pretty small in our night sky. So they're not the coolest things to look at with our telescopes. Things that are really cool, in my opinion, are things like the stars and nebula. So those are things that are inside our galaxy, but beyond our solar system. So nebulas are clouds of gas and dust that you can explore in the night sky. Some of them are places that stars are being born. Others are places that stars have exploded and died and have let off their gas from their leftover stars. You can also look at star clusters, areas of the night sky where there's lots of stars together. Beyond our own galaxy, the Milky Way galaxy, we can look at other galaxies. We can take images depending on the night, things like our local neighbor, the Andromeda galaxy, or farther away, things like Whirlpool galaxy and Pinwheel galaxies, lots of things to explore. So choose your own objects. Different objects are gonna have different opportunities that you're gonna have to request from the telescope. So I'll tell you what that means in a second. So like I said, some of my favorite things are the nebulas. I'm going to take a picture of the Lagoon Nebula. So when you get here, so the Lagoon Nebula, the only field of view that our telescopes take an image of this in is the normal field, so that 1 degree. So when we look at this, it's about, now I stick my finger out at arm's length, it's going to fill up about my pinky nail amount of night sky. So I'm going to take a picture of the Lagoon Nebula. And like I said, nebulas are pretty dim in the night sky, right? When we look up, we don't really see them. But another thing I'm going to give you a hint at. So the moon is smaller, a little smaller than the 1 degree. So it will fall within the 1 degree field of view. It's about a ½ degree total. So this is about the same amount of night sky as the moon, actually a little bit more, but we don't see it with our naked eyes. And that's because it's really dim. So maybe it's 30 seconds of exposure time. Oh, what you'll see here is that our interface actually guides you to taking an image with the best exposure time for that particular object. So we really need to gather a lot of light for nebulas. So I think we're going to go with 60 seconds. This is one of our ways to make this a little easier for users. So hopefully it'll guide you towards choosing the best options for the object you're choosing. And I'm going to take it in multiple filters, meaning I'm going to take it through that red, green, and blue filter like I talked a little bit before, so that later I can put all those images together and create a true color image of the night sky. All right, after that, I'm going to hit continue, and all you need is an email address. Whether you as one teacher wants to use have your students use one email address, or each can use their own, and then you can choose to or not fill out the rest of the information here. I'll fill it out real quick. And then you just hit submit. And your image has been submitted. Your request has been submitted. And you'll see this confirmation here on the screen. And it tells you a little bit about the object that you took your image of. So as you can see, the nebula that I took an image, that I'm taking an image of is a star forming region. So that cloud of dust and gas where stars are being born. It's 4,100 light years away, which means it took over 4,000 years for the light from that nebula to reach our telescopes. And it tells me what I took the image of. Now, these are real telescopes, meaning I'm not going to get an image this second. The telescope still has to take the image. So it's actually not going to be until tomorrow, probably around 1 o'clock, when our 1 p.m. Eastern time, when our telescopes distribution happens. So we've got to wait for the telescope to jump into action tonight and take that image, and then tomorrow, once it's done sorting, it'll send you your image in your email. So let's go back to our presentation. Now that we've all taken some images, feel free to pause me for a minute and take some more images if you want. Like I said, this is a free open website to anybody, and you can take as many images as you want. You're not going to overwhelm our telescopes. So let's get back into our presentation. So we talked a little bit about some of the features of our telescopes. I want to walk you through an activity that I like to do with students, and it really has a big impact on their understanding of telescopes. It's called Kinesthetic Telescope. Obviously, I don't have enough people in my room to do it, but what we do is we assign everybody an object that they're going to be in the telescope. Everything from the object in space emitting light, right? So there's some object out there emitting light, a star maybe, sending off light. Then we have people act as photons of light. So there are those photons of light coming towards our telescope. There are photons going in every direction. You have someone act that out here, right? So photons, we're only going to see the photons that come towards our telescope. Then you have two students get up, and they can be the aperture or the opening of our telescope. So one person on each side, wherever our telescope opening is. Then we need someone to act as a mirror. So they're the person that directs and focuses the light towards our detector. So you can have someone there directing the light. And then we have our shutter. Somebody has to act as our shutter and decide how long are we going to let light in for? Do we want a lot of light? Are we looking at something dim or just a little bit of light? So you have a student there, count for 30 seconds, cut off the photons of light that don't make it if it's after 30 seconds, they don't make it to our detector. Then you got to have someone that's the detector receiving that light, measuring how much light came to them, and they can tell the rest of the group how much light actually made it. And then once that light gets to the detector, that is recorded and creates the image of the object. So this is a really useful activity, and I've shared it in an online tool here, so you'll actually be able to see the full downloadable curriculum piece to run this activity with your students. And I think what's really important to understand is that it's a great way to help learners understand how telescopes are light collectors and not magnifiers, right? Oftentimes we think of them as magnifying. Maybe if you've looked at a telescope with your eyes, like a eyepiece, you think about the magnification. But when you think about it, many of these objects that we're looking at are light years across. They're huge. So we're not magnifying something that's bigger than our whole solar system. What we're doing is collecting as much light from it as possible to be able to see it. So I want to take a quick pause again here and ask you to reflect on, what does a telescope do? Look back at your answers from a few minutes ago and maybe see if you want to add anything or amend to your definition of what does a telescope do. Give you a second to do that. Feel free to pause me. All right. So, like I said, our real telescopes are gonna hop into action tonight and take your image. In this beautiful picture, it's really sunny in Arizona. These are two in Amado, Arizona. But one thing you might not see on our telescopes that maybe are familiar with if you've ever seen pictures of ground-based telescopes is a dome. There's no dome over ours. And that's because our telescopes are sealed to protect them from the weather. And they'll take images, whether it's rain or shine. They'll point where the object should be at the night sky. And if there's a cloud there, they're still going to take an image. Unlike the professional instruments, which just won't take the image if it's raining or shining. Ours are weatherproof. So if it happens to be rainy in Arizona and Cambridge tonight, or cloudy even, you might get an image that looks like this. And that's okay. That's what happens to the scientists too. That's one of the reasons we have telescopes out in space, is to limit the amount of interference we get from our own atmosphere. So if you get an image back tomorrow that's cloudy, just take another one tomorrow. That's the same frustrations that scientists can feel. So if you see something that looks along these lines, it's not your inability to understand the image or process it. It's just a cloudy image, and that's okay. Take a bunch. All right. When you do get your image, it'll come in an email. There'll be a link for you to open up. And the website will initially look like this. This image here in the center is a preview GIF image, a GIF file. It's not in the format that our astronomers use, and astronomers use something called a FITS file. And that's the one that has all the important data, because images are data. And so you actually want to, in the upper right-hand corner here, click on the thing that says .trifid nebula.fits, or whatever image you took .fits. And these numbers after that are just the date and time that the image was taken. You can either download that image if you want to be able to look at your image for a really long time. The images only stay on online for us for 20 days. Or you can click on this little button here that says view this in JS9. And that's what we're going to do in a second. I'm going to walk you through what's going to happen first, and then we'll view our images in JS9, which is the astronomical tool for image processing for astronomers. Like I said, this is something that astronomers have to do as well. They have to take those pieces of data that come from the telescope and make them into something beautiful that we can see, or something that they can process and understand in other ways. These are jobs that people have as well, making those beautiful NASA images that you've seen. On the screen here is an image of one of my former colleagues whose job it is to make beautiful astronomical images from the Chandra X-ray Observatory. And we're going to use tools just like similar tools that he's used to use. But this skill of image processing that we're going to learn about in a second isn't just for astronomers. It's across the fields of science, the STEM fields out there. Everything from energy home audits, looking at infrared and leaks, where's the heat leaving from your building, to X-ray imagery at the hospital. Having to understand digital images is a critical skill, STEM skill for many careers. So, like I said, images are digital. They're just numbers. The images that we get back from scientific instruments. This is a simplified field of view from our telescopes. Ours are about 1 million pixels. This is a lot less. I want you to take a second and look at our fake detector here on the left. And imagine that everything that's white, labeled number 1, is painted white. And everything that's labeled number 8 is painted black. And then everything on that gradient in between is shades of gray. Do you see an image? Does anybody out there take a guess of what that image might be? I'll point out we've got an 8 and some 6s here, an 8 and some 6s here, and some 8s here. Give you a second to think about it, look at it. If anybody out there guessed, this is a smiley face, right? Images, these are just representing how much light fell on each pixel of the detector. So in those areas where there was a 1, basically no light fell on that part of the detector. Areas where there were 8s, 8 photons of light fell on that piece of the detector. So there was more light in that area. And that's all we're going to be doing with our real images of the night sky as well, is better understanding where the light fell and what does that tell us about that part of the night sky. So we're actually going to open up the instrument, or the image processing tool called JS9. We're going to go back to microobservatory.org. You can either watch me once, follow along. I'll also show you where you can find some tutorials. So after this presentation, you can go back and watch some specific tutorials for learning how to do image processing. All right, so change the screen again. Now we're still at that Observing with NASA page, and instead we're going to go to Analyze Images. Now this is going to open up JS9 4L, which is the tool for astronomers. It's got a lightbox tour to walk you through the steps. I'm going to close that and take you on the steps myself. Just shrink my screen a smidge here. I can't see the full thing. All right, and if you want to watch that guided tour after you close it, you can always open it up again. So in JS9, because we know sometimes we're not also patient to wait for the next day to get our images back, we've got a set of archived images that you can look at that includes both a bunch of micro observatory images taken with our telescope, as well, if you scroll down, to some NASA images, so data taken from real NASA telescopes that you can process yourself and see and explore. I believe I've already got a Lagoon Nebula image opened up, so that's what I'm gonna process for you guys as you follow along. So the image opened. It doesn't look very exciting. It's all black. What does that mean? There's a few bright spots, and I'm gonna move my mouse around, and I want you to look at this thing called the pixel value up here in the right-hand corner. I want you to look at this number as I move my mouse around the screen. Go over down here to 339. It's pretty, not 3/4. I'm gonna move it closer to these bright star spots, getting 380, 396. Oh, 4095, a lot higher when we get to that really bright spot. And what this pixel value is telling us is how much light fell on each part of the detector when we left it open with the shutter open. So where was there more light? Where was there less light? That's what this pixel value is telling us. But I want to see what that really means. So we're actually going to do some image processing. One of the first things I like to do is change the low brightness value. And what that means is, like I said, even in these places that look really black, there's still light there, right? Light still fell on it. It's because the night sky isn't perfectly black. There's still always a little bit of light, even in some of the dim places. So I'm going to put my mouse in a corner that doesn't look like it has anything. Try a couple. Looks around 340 is kind of that low pixel value. So I'm going to set my low pixel value to that number and hit enter. Not much changed. That's because there's another secret trick we want to do. You want to go up to the scale and change our scale from linear to log. Okay. And out of nowhere, you've got a nebula, right? You've got this beautiful thing. And what's happened is we're just changing where we put those shades of gray. Remember how when we were looking at that image of the smiley face, we had shades of gray between our values 1 and 8. Well, there's a certain number of shades of gray that our computers can see and our eyes can see. And so we've got a limited amount of space to do that. And so when we move from linear to log, we're just taking all those shades of gray and squishing them down in to the dimmest part, because as you notice, 357 is not much above our background night of 342, but there's a lot of detail in here. So we want to use all those shades of gray to see that little bit of detail. To bring out a little more detail, I'm actually gonna bring down my high brightness as well and see more of those details stretch out. All right, so I think that's looking pretty good. Some things that you might notice, there's these things here are called these dust lanes, these darker areas. That's areas where there's so much dust in this nebula that the light can't get to us, so it looks darker. There's actually more dust in some of these areas. You'll see lots of little stars in here. This, like I said, this is a star forming region or an area where stars are being born. All of this gas and dust is condensing. When it gets dense enough, a new star forms. So that's the basics. Sometimes we also like to make them a little prettier for fun. And so I'm gonna actually add some colors. We've got these color maps that are just fun. Instead of just painting in shades of gray, we're gonna do painting in other colors. Let's see, let's try watermelon. So one thing I'm going to point out to you when I do this is this color bar at the bottom. And this is kind of like our key to the paint by numbers. So anything that has a value between 341 pixels and I'll say like 352 maybe pixels is being painted in these shades of green. And then as we go up, things between like 360, maybe 400 are being painted in shades of pink. Only the really bright things are being painted in yellow. So that's this particular color map. Maybe I'll pick a different one. Maybe let's try Magma. This one's really nice. And again, you can look, purple are the shades between, 340 and 360, or anything that had that many photons of light are being painted that color. And that's all we're doing here, is choosing how to display that data, right? So how much light fell in one place, and what color do we want to represent that as? We're representing the data in a certain way. I'm also going to point out this color map called Viridis. This one is specifically designed for students who are colorblind. So if you have any students in your space that are red-green colorblind, this is a great one for them to use to be able to really see the details in the images that they're looking at. But I'm going to go back to, let's try Fire Sky. That one's kind of fun. Really kind of brings out the dust lane. So that's another thing to point out, is different color maps bring out different details, right? Shows you different parts of the nebula, and that's one really fun part. So it's creative, you get to be artistic here a little bit, but also choose what parts of your object do you want to display. There's also this region tool, and you can add text, so you can label it. You just double click when you open it, click region text. I'm gonna label mine Lagoon Nebula. And then you just hit apply. And you can close that box. And there we go. You can also change the color of your text if you want in there. I'm not going to do that right now. And there's my image. And maybe I want to save this image. And so you can go to image and save as PNG or JPEG. Don't save it as a FITS. The FITS is the raw data. It's only going to save those numbers. And FITS files can only be opened in tools like JS9. So if you save it as a PNG, it'll download wherever your things download in your computer, and you can open that up. I'm not sure you'll be able to see mine because it's not in the shared screen, but you can open that up and save it. Maybe you want to share it with, I think we can share images in this chat, the text space. So share the images that you process with the rest of our group. All right, so now we're going to go back to my presentation for a little bit. Feel free to play around with that a little bit and come back to the presentation if you want. I'm going to share with you now. I'm going to walk you through a few things you and your students can explore together. So there's some investigations you can do. You can investigate moon phases. We like to create moon calendars, so taking an image of the moon every night, with a caveat you might miss a night or two because of bad weather. You can even create little GIF videos if you want. There's a tutorial on the Micro Observatory page on how to do that. So this is a set of images taken over the course of about 1 month, walking you through the entire moon phases, and your students can explore that. You can actually see how it gets a little bigger and smaller as the moon gets closer and farther from the Earth in its orbit. Just a little bit, but it is visible and it is noticeable in measuring. You can explore changes over time. So here we actually have an image of Jupiter. Jupiter is actually this really bright object here with the big jets coming out. Those jets are actually an artifact because Jupiter's pretty bright. It's small, but it's pretty bright. And we want to look at the moons, the 4 what are called the Galilean moons. These are the moons that Galileo first observed, although really what we mean was the first to document observing. You can see his drawings here. So he was trying to understand how those moons went around Jupiter. And so you can see those as well as they go around Jupiter here, but they're much dimmer compared to Jupiter. So what we actually had to do here is overexpose Jupiter a little bit. And when too much light falls on one pixel, those photons of light actually fall over into the pixels above and below it. And so anytime you see these stripes on a star, that just means, or any object that you might take an image of, that that particular part of the image was overexposed and a little extra light fell into the wells beside it. But you can see this is another GIF, so video created with a couple images. If you take an image of Jupiter's moons, you'll get 3 or 4 images back, and if you blink them, you can watch them move. You can see how these images are actually moving, these 4 dots. Looks to me like the 2 in the back are going around the back of Jupiter, and the 2 in the front are kind of coming around the front here. So that's something your students can explore. They can see the motions in our night sky. They can explore sunspots. There's not a ton right now. The sun is in what's called a solar minimum. There's not a ton of sunspots, but they can watch the sunspots move across the surface of the sun. They can explore scale. One thing that is pretty common is textbooks and images on the web are all taken with different fields of view, and it's really hard to get a sense of how big something is in the night sky. And like I said, every image, if you take everything in a normal field, is 1 degree. It's all going to be the same amount of the night sky. So in this picture, you can see the moon and this star cluster about the same size, but when we look up, we don't often see this because this is much dimmer than the moon. You can also see here in the bottom right-hand corner, that's Saturn. It's pretty small compared to the moon in the night sky. But there it is. That's how much space it takes up. And so you can start comparing how big some of these things are in the night sky. Another activity that you and your students can do together is something called Strobe Poetry. So if you have with you maybe some sticky notes or a piece of paper you can rip up, I want to ask people at home to write down some words that you think of when you see this image. Let's see, can I? No, I can't, not right now. I was going to try and draw some images, but I don't know how to do that very well. So write some images. Some things when I see this, I see, yeah, write some images, write some words. I see things like, here words like billowy, pink, gray, floating. Think of some images, think of some words that reflect the imagery in front of you and write them down. Ask your students when you're together to all write them down, put them up on a big whiteboard together and get all of these different words. Ask them to really be creative and thoughtful in the types of words. Sometimes you can get things like cotton candy, or sometimes I see this and I see a squid. That's what I see as a squid. It's kind of squid shaped. So nouns, verbs, adjectives, get all of those words together on a bunch of Post-it notes, whatever way works for your classroom, your space, and then turn it into a poem. Have people move them around and create a poem. Or you can do a more structured poem and have your students write what they see. This is a poem from one of our past students. I took a picture of the Orion Nebula. It's a cavern of roiling dust and gas where thousands of stars are forming. It's like you can go to another world. Right, so that's what this student thought when they wrote this poem, right? So you can be more creative, more descriptive, whatever you want to be, but this really helps students to look closely at their objects, to be thoughtful about what they are. It's a great way to deepen their engagement with the images. So now we're going to take one more break. We've looked at some of the curriculum, some activities you can do. I want to have you take a moment to go to this YouTube video. This is a video about one of our specific ways of engaging with the micro-observatory telescopes through something called Youth Astronaut, or Youth Astronomy Network. It's an online community for engaging with our telescopes, our digital processor, each other, our scientists, and myself and my coworkers. You can watch that video, see some of our past students' reactions to engaging with the telescopes, and really kind of explore what they know. Youth Astronaut has a few essential programs that I think are valuable no matter whether you join in the Youth Astronaut community or not. We ask students to control the robotic telescopes, take and analyze images. That's one of the critical parts of being part of the Youth Astronaut community. That's something you can do on your own whether you join us or not, using our telescopes. And then interpret those images in some way. Our students that participate in Youth Astronaut have work aimed at an authentic capstone project, and those can take many shapes. They can be small classroom exhibits, they can be virtual online spaces. We've had people create things like wikis where students display their images with some text and some descriptions. There's a lot of different ways these capstone projects can take place. They can be presentations, but student-driven authentic inquiry with the capstone project really gives students ownership of what they're doing. We've seen a lot of great results from those. And then we encourage STEM and STEAM and arts integration in our Youth Astronaut programs. So seeing the relationship between astrophotography and digital photography, learning about light and color, These are all things we also have extra curriculum for on Youth Astronaut Community. These are all great resources and things that support student learning. Like I said, Youth Astronaut is an online space for all of this work to happen together. As you can see, this is the interface looks like. There's resources, places for students to get to know our scientists at the Center for Astrophysics. There's forums to talk to each other, to talk to the staff, talk to scientists. It's also a secure space, so only teachers can enroll their students, and you have to sign up to enroll yourself in Youth Astronaut. So it's a nice, safe space for students to explore together. Another really great part about the Youth Astronaut community compared to using our Observing with NASA open portal is that each student gets their own access to the Youth Astronaut community. They get a username and password, and all the images they take are kept together in one space. So it can get a little overwhelming with those emails with each image that a student requests, keeping track of them, encouraging your students to keep track of them. So every image they take is saved for 1 month in their online space that they can access easily, download to their own computer if they want to keep any of them, but it's all there in one space for them. So it's a lot easier to coordinate and organize. To give you a sense of what students are learning while doing these astronomy investigations, learning about the night sky with us, students who have participated in our Youth Astronaut community talk about, they self-identify some of their learning. We ask them to tell us one thing they learned. They talk about some astronomy and science content. So they're learning astronomy and science content. And many of our educators that engage these students didn't know a lot of content beforehand, so they're learning these things together. They talk about telescopes. They better understand how they work. They talk about image processing. Also, a lot of students just mention having enjoyed the experience and having a positive impact on their outlook of science. Briefly going to show you this slide. I know it's a kind of not the most exciting graph to look at, but one thing I want to tell you is that this project, when it first started, was also a research project. And students who engage in the core activities of Youth Astronaut, like I talked about, telescopes, image processing, asking questions, see an increase in their STEM career interest, their astronomy knowledge, and their science identity. So whether or not they see themselves as a person who can do science and like science. All of those increase when they participate and engage in our core activities. And then for the programs that engaged in making those connections, those art, history, everyday connections, their students also saw increases in science identity and STEM career interests. So those programs were able to increase that as well. I think these are really key ways that using these telescopes and increasing student connections that has a positive impact on student connections. So like I said, we're promoting student STEM interest by using telescopes. So what to do now? You can, like I said, go to microobservatory.org, explore the telescopes, the image processor. There's also a number of other curriculum support materials there for you to engage with. We also partner in something called Universe of Learning. You can go to universeoflearning.org. There's a number of extra resources there for you to engage your students in astronomy learning and content. If you want to join our Youth Astronaut community, it's open to everyone. I've got a flyer about some of the things that are available to you in the online space here, so you can download that. There's recorded webinars, more of this, more deeper learning. There's spaces for you as teachers to have conversations beyond our online conference here. So if you want to keep talking about space and astronomy, there's spaces for that. And then there's places for you to enroll your students in here. And like I said, go to surveymonkey.com/r/youthastronautNAA, and you can sign up to engage your students in that online space. We also engage our scientists there. All right, so as we wrap up, those are the things you can do next. I just want to ask you to take a second and reflect on how your knowledge of astronomy and the tools used for doing science has changed. Have you gained any new content knowledge? Do you now know more about how telescopes work or digital imaging works? I also want to take a second to reflect on what kinds of engagement strategies in STEM learning did you experience or learn about today? I know we didn't get to do all of the activities we talked about, but hopefully you started imagining how your students might do some of those activities. And what are some of those engagement strategies? Because many of the engagement strategies I talked about in using in astronomy today can be useful across your teaching experiences with your students. They don't have to just be limited to astronomy. Things like capstone projects, arts integration, kinesthetic activities. So what kinds of things did you learn about today? If you want to share those in the conversations below, I'll be making a post about that. I'd love to hear from you. Or maybe you've got some other ways that you could see using these tools and furthering that engagement. So take a minute to reflect on that. And thank you for joining me. You can follow us at MicroObs. We have a Twitter and a Facebook, and hopefully follow up with any questions as well. I look forward to talking to you in these online forums as the online conference proceeds. And thanks for joining me today.